Hello everyone. Today is the day 12 of 75 hard research challenge. I'm going to talk about what I did yesterday, that is on day 11. So yesterday I studied something called quantization in large language models. Specifically I studied linear quantization and Pytorch and data types. So I'm going to talk about these two topics in today's video. Let's get started. Okay, so let's first see why we need quantization. So most of the models these days are very large in their memory footprint. For example, if you have a model with 10 billion parameters where each parameter is represented using floating point 32, that implies it uses 4 bytes of memory for each parameter, then that would imply that you will need at least 40 billion uh, bytes, right? So that translates to a very huge number, right? And for these reasons, what happens is that most of the researchers which do not have access to high bandwidth or high memory GPUs, they end up not being able to use this in their smaller projects or to do some other type of research that does not require this much size, right? But does require the quality of the performance that large models deliver, right? So what is the option for this? What do? We would like to somehow shrink the models to a smaller size while maintaining their performance to the similar degree, right? So one of the easiest way to do it would be model compression, where what we do is called so one of the ways is called pruning, where we remove some of the layers in a model that do not affect the output that much. So how do we do it? For example, we will set a metric like we will say that there is a the magnitude of the weight is very low or the norm of the weight is very low, and we will remove certain either we remove certain neurons or the connections from one neuron to another, right? Another way of doing this would be to do something called knowledge distillation, where we have a very large model with us and we have a very small model. The large model is called teacher, the smaller model is called student, and other than training the student model on the original laws, right, we also add some form of supervision between the teacher and the student, right? Some log term L2. Okay, so we'll not go into the details of this. We will focus on something called quantization. Okay, so let's say you have a simple linear layer where you have x as input, you multiply it with a matrix W and add bias vector B, then you pass it through a non-linearity, right? So what we can do is that we can either quantize, and the output of this is known as activations. Okay, so A is the activations. So what we can do is that we can either quantize the weights W and B, or we can quantize the activation itself, right? So quantizing a model from floating point 32 to int 8 precision will introduce some quantization error, right? Okay, and our goal is to lower this error as much as possible. Okay, so let's say you have 9 parameters with you and you represent it into floating point 32, then you end up with having 36 bytes, right? But if you represent the same 9 parameters using integer 8, then you are left with only 9 bytes. So this reduction in the memory leads to something called quantization error, and we would like to minimize it. Okay, so now let's see what are the various data types available in PyTorch. For example, there is, or in general also, that there is unsigned integer. For n bits, you can represent 0 to 2 raised to power n minus 1 numbers, right? And this is some very basic fundamental like computer science 101, or probably lower than that also. Similarly, for signed integers, for n bits, you can represent minus 2 raised to power n minus 1 to 2 raised to power n minus 1 minus 1. Because this is called 2's complement representation, there is one extra negative number that you can represent as compared to the positive numbers, because one of the values will be occupied with the 0. Okay, so this is the representation for that. If you have 8 bits with you, first bit to 8th bit, then the least significant bit, that is on the rightmost of this particular vector, 2 is represent 2 raised to power 0, then 2 raised to power 1, and so on till the last bit, which represents minus 2 raised to power 7, right? Okay, if you want to see what are the ranges of various data types in Pytorch, what you can do is you can do torch.iinfo, and then in the bracket you can find like pass the data type that you want to see the details of. For example, here we have given the parameter as torch.uint8, that is unsigned int 8. Okay. Let's focus on floating point representations now. So floating point representation has three parts. One is sign, second is exponent, third is fraction. Sign represents whether the number is positive and negative and takes 1 bit. The exponent represents the range of the number, and fraction represents the precision of the number. Okay. So for example, here is a small table. Here we have floating point 32, 16 and something called BF16, right? So sign is again it represented using 1 bit in each of these. For exponent, FP32 uses 8 bits, this uses 16 and this uses 8, right? And apologies, this should be 16. Okay, so and all these bits eventually add up to either 32, 16 or 16, right? And similarly, you for checking the details of a floating point data type, you can use torch.finfo and pass the floating point that you want to see. Okay. Now we'll see what is downcasting. So downcasting is moving from a higher precision or higher data type to a lower one. For example, if you want to move from FP32 to BF16 or FP16. Okay. So the advantages is again a reduced memory footprint and increased speed. Why is the speed increasing? Because now the number itself is represented using 1 byte, which was earlier represented using, let's say, 4 bytes, right? So you have lesser amount of bits to multiply and add and so on and so forth. The disadvantage, of course, is that now you have lower precision, right? Okay. So there is let's focus on what is linear quantization. That means how do you downcast a higher let's say floating point 32 to integer 8. Okay, so in this case, let's say you have integer 32 number that you want to downcast to integer 8. So how do we go about this? Let's say this is the original range of the number in the higher data type, and this is the range of the number in the lower data type. So what you do is you map this Rmax to Qmax, Rmin to Qmin, and then the 0 point on the original data type gets mapped to some point z in the quantized range. Okay, so what is the formula that governs this? This is simply a linear transformation. That means that is why it is called linear quantization. It says that R is equal to S into Q minus Z. What is R? R is the original value somewhere in this line. Okay, Z is the quantized value representation for 0 on the original range. Q is the quantized value. For example, if you have R here, somewhere here, let's say Q is getting mapped, right? And S is called the scaling factor. Okay, the scale is there. Okay, now we will see that to solve these equations, how do we get the value of S and Z, which are constants, right? So for S, you can see that S represents the scale. So it makes sense that what is the magnifying scale or downsampling scale that you are using? Simply you do take the ratio of R max minus R min. That means this particular length divided by this particular length. So, okay, so that's what we have done here. Similarly, for Z, it turns out to be this particular value. Okay, it turns out to be this particular value. Okay, so what does that mean? That means that 0 point in the quantized line is represented by you take the Qmin here, you subtract the Rmin by S. Okay, so Qmin minus Rmin divided by S, you round it and you take integer, because integer and rounding because it is represented using a in the quantized scale. Okay, so essentially what you are doing is that you are asking where does Rmin land into the quantized range. You subtract Qmin from it and you say that You subtract q min, you subtract r min by s from q min, and you get the value of z. Okay. Okay. Uh, to quantize activation, we can also find the range of activation because it depends on the input. So for example, in the case of weights, you already know what is the maximum and minimum range. It may or may not be right, but and what is the exact value of the weight you already know because the model has already been trained, right? But in the case of activation is the output of the linear layer or non-linear layer in this case, right? So that means that it is a function of the input as well as the weights. So activation will continue to vary based on the input. So what you can do is you can find what is the minimum and the maximum range for the activation by passing the dataset through it, or some portion of the dataset or a representative dataset through it, and get the range and quantize accordingly. Okay. Uh, so there is something also called quantized aware training. In this case, what you do is that while doing the forward pass, you do the forward pass on the quantized weight. So for a given model, you keep two versions of it. One in, let's say, int 8, that is the quantized version. One is the original, let's say floating point 32, which is the original version. Okay. So what you do is that you do the forward pass on this. Okay. But when you do the backward pass, you use the weights that were not quantized yet. Okay. So and you do the backward pass based on the gradient computed on this. Okay. So there are multiple various ways to implement quantization aware training, and we will look into these methods in the upcoming lectures. Thank you.